Most structural engineers today know software, but very few actually know how to design. I am a practicing structural engineer, and in this video, I want to share how steel structure design thinking works in practice. In the next 30 minutes, I'll explain how to think like a structural engineer while designing steel structures. This is not a software tutorial. This is about engineering judgment that applies no matter which software you use. Let's start by discussing why thinking matters more than software. Software has no engineering responsibility. Software does not understand reality. It only does what you tell it to do. If assumptions are wrong, output is wrong, and software will not warn you. Wrong input will give you wrong output. Let's assume that you model this structure. You assign certain supports, pin connection, roller connection, fixed connection, whatever. You assign certain loading to your model. Behind these loadings and behind these support conditions, there are many assumptions which are made by the software. Most beginners don't even know what assumptions they are making. Software hides these assumptions behind checkboxes. Whenever you assign any kind of pin support, or whenever you assign any kind of loading, or when you assign certain specifications to the members like member releases, there are certain assumptions which are made by the software. And if these assumptions don't match with the actual thing which are constructible on site, then there will be errors. Most design errors are not calculation errors, they are assumption error. The thing what you assume while you are modeling, that should be practical on site. If it is not matching, then there will be error. Next, software cannot judge structural behavior. Software will only give you forces and utilization. Whenever you model, you will get what are the forces in the member, and if you design these elements in the software, you will get the utilization ratio. The software will not be able to tell you if these forces are practical and if your member will actually carry these forces. Is this force realistic? Are the connections buildable? Whatever connections you are trying to make in the software, are they practical on site? These things software will not be able to tell you. Next, there is a major difference between steel and RCC structure. Steel and RCC. Steel structures are extremely sensitive to wrong thinking. Some of the properties of steel is a slender material, it is light in weight, it is highly sensitive to buckling, and stability is also a big concern for steel structures. Steel structures are long members, they are mostly slender, so all these parameters what we discussed right now, these affect your structure. When you compare the same thing with an RCC structure, RCC structures are huge structures, the self weight is large. Most of the errors, most of the thinking issue, they are hidden behind this heavy mass of the RCC. Because of the huge self weight of the RCC itself, most of these issues like buckling and stability, they hide behind the heavy mass. So even if there are certain issues with the thinking, still your structure will not fail. Comparing it with steel structures will fail because you have not guessed the right thing. Real failure don't happen due to formula mistakes. Most failure occur due to wrong load path, ignored stability, poor connection, not because someone forgot a formula or someone used a wrong code. The purpose of this video is not to be anti-software, but it is to be pro-thinking. The goal is to teach how to think before you model, so that software becomes a tool, not your master. If you fix your thinking, software automatically becomes a powerful tool. The next step, start with big picture, not the member, system level thinking. A steel structure is a system, not a collection of beams. A steel structure is not a beam or a column or an individual member. It's a load carrying system. First question, why does this structure exist? Let's assume this is a structure what you want to model. The first question what you should be asking is, what is the purpose of this structure? Is it an industrial structure? Is it a steel warehouse? Is it a power plant? Or is it a pipe rack system? What is the function of this structure? Not just the geometry, understand the overall function. What will be the clear height of your structure? What will be the clear span of your structure? What will be the loads which would be coming on your structure? What would be the general openings for your structure? All these questions you should be asking before you start designing it. Think in terms of zone, not just member. You should mentally break your system, break your structure into various zones. You could have a roof system, vertically load system, lateral load system, foundation interface. Each load system has certain members assigned to it. Maybe when you are building a roof system, you could have some rafters and some purlins over it. This will be part of your roof system. Vertically load system, you will have your rafters and columns which will transfer the force to your ground. Lateral load system, there could be bracing system which would transfer your load to the ground because of the wind or seismic action. Or finally, you could have your base plate which will finally transfer your load to the footing. So in this way, you have to break your structure into zones: roof, vertical load, lateral load, foundations. You should identify the primary load resisting mechanism early. How will the gravity load be resisted? How will be the wind load resisted? Seismic load. How will be the portal action in your structure? What would be the bracings what you would be providing? Will you be providing a moment frame? If you don't choose your system properly, the software analysis will automatically choose one, and the randomly chosen system by the software may not be what you have assumed. Next, clear span control everything in steel. The span of your frame, the span of your structure will control most of the things in your structure. The span is very important. Also, the spacing between the frames is important. Let's assume you are having multiple frames. The spacing between these frames is equally important. The portal frame span and spacing defines the individual member which you are assigning to it, whether it is a column or a rafter. Depending on the span and spacing, the size of your column and rafter will change, and this will drastically increase or decrease the overall tonnage of your steel requirement. Next, don't just design for today. Think about the life of your structure. Steel structures are modified multiple times during its life. Your thinking must allow this. Think big. Think regarding the future expansion, the future equipment load what could come on it, the additional loads, the maintenance access to your structure. See, when you are designing, whether the thing what you are considering is practically possible on site. Is it constructible? Assembling of your structure, dismantling of your structure, all these things you should think. Once the system is clear, the next step is to understand how load actually moves through your system. Next, visualizing load flow. Load flow is the language of the structure. How load travels through the structure. Load don't disappear. They move member by member until they reach the ground. Every load you apply is asking one question. How do I reach the ground? Think in clear load path. Let's assume this is the structure. Now whatever load you will be applying on this, it will follow a certain load path from roof sheeting to purlins to rafters to columns and finally to base plate and foundation. Separate gravity load flow from lateral load flow. In a structure, the gravity load are the loads, generally the lead load of your structure and the live load what you would be applying on the structure. These loads are very simple. They act in the direction of gravity and your vertical systems are capable of carrying those loads. The next important kind of load flow is the lateral loads. These are the loads which come from wind action, seismic action or temperature effect. You need proper load path for these loads to travel to the ground. Generally, they travel through bracings. Many of the systems are very good in gravity loads but are very bad in lateral loads. Most of the failure which occur, they are because of poor lateral load path. Many of the structures are strong vertically, but they are weak sidewards. Load does not only follow the connection of your member, it also follows the stiffness of the member. Two members which are connected will not transfer the same load to the another member. The load follows the stiffness of the member. Stiffer the member, higher will be the load transferred to that member. Flexible the member, lesser will be the force attracted by that member. So the load transferred from one member to another not only depends on the connection of the member, but it also depends on the stiffness of the particular member. Thicker member, heavier member will carry more force than a lighter member. Identify compression and tension early. You should understand whether your member is carrying a compression force or a tension force. Let's assume this is the member and these are the cross bracings. Whenever there is any kind of lateral load coming on this particular member will be under compression and this particular member will be under tension. The difference between compression member and tension member. Compression members can buckle easily. Buckling is critical in compression member. Tension members are important because the connection is critical in these cases. The members which are under tension, for them, connections become critical. There is also reversal of load. This cannot be ignored. A particular structure may have various loads coming on it. Because of force in one direction, a particular member could be under compression and the other member could be under tension. But because of reversal of loads, the same structure will have members under tension in one case and members under compression in other case. So these load reversals cannot be ignored. So these are all the points which you should keep under consideration when you are visualizing your load flow. After you understand the load flow properly, the next step is choosing the correct structural system. The next step is choosing the right system. There is no best system, only a suitable system. You do not have a universal best system. Every system is a response to its constraint. Right system depends on the type of structure. The type of system depends on the span of your structure, the height of your structure, the purpose of your structure, the load your structure would be carrying, the cost constraint what your structure would be having, the construction methods what you would be adopting, the soil condition of your structure. All these things together will define the correct system for your structure. First, you should decide how your structure will resist lateral loads. Will you design bracings to carry your lateral loads, or will you design a portal frame to carry your lateral loads, or you will be defining a moment frame to carry your lateral loads? Once you decide how your lateral load will be transferred, half of your work would be done. Now let's understand the difference between a portal frame and a braced frame. In portal frame, generally you have a frame which will carry moment, and this structure is having fewer members. The sections are heavier and they will be able to carry large moment. Comparing it to a braced frame is a structure which will have large number of members. The number of members will be more. These members will be lighter in weight. Braced frame, axial force is critical. Portal frame, moment is critical. A same section could be a portal frame in one direction and a braced frame in another direction. Let's take an example of a general structure. This is number of frames, portal frames, and these portal frames are connected by bracings in the other direction. So when forces are coming from one direction, the portal frame will be able to carry them, but when the forces are coming from the other direction, in this direction portal frame will not be effective and braced frame will come into action. So a same structure will act as a portal frame when wind is acting in one direction and act as a braced frame when wind is acting in another direction. Next, trusses are not always cheap. Many engineers have this assumption that trusses will always be cheaper. Let's understand. Trusses reduce bending moment, but they increase fabrication cost, they increase the number of connections. So this is not always cheaper. A truss is having lighter members, but the number of members will be more. Because it has more number of members, the number of connections will be more, and the fabrication cost will be more in case of trusses. The steel weight will be less, but the overall fabrication cost and number of connections will be more. This will result in maybe higher cost. So trusses are not always economical for shorter span, for lower heights, for tight schedules. So this is the misconception. Next, stiffness versus weight. Lighter sections are more flexible. More flexible members are subjected to higher deflections, higher vibrations, and P delta effect will be more. Now let's quickly understand P delta effect. If this is a column, this column is subjected to some force P. Because this is a lighter member, this column will tend to buckle, tend to bend, and this will be the final bending. And the force will still be acting at this point P. Because of this buckling, there will be this movement, there will be this deflection delta. Because of this P and delta, there will be one additional moment which will be generated. This additional moment which is generated, it is called as P delta effect. Lighter sections are more subjected to P delta effect. That is why it is not always economical to have very lighter sections. Sometimes stiffer members give economical solutions as well. Sometimes slightly heavier sections perform better than lighter sections. Steel is often governed by stiffness, not always strength. Let's discuss regarding redundancy versus efficiency. A highly optimized system will be less redundant. Optimum system. A highly optimum system will be less redundant. This means that this member will have lesser members which are subjected to zero forces or lower forces. In this case, all the members of the structure, all the members of a particular structure will become important. Even if one of the member fails, even if one of the member is subjected to some adverse loading, unaccounted loading, and if there is any failure on these members, the whole system could collapse. Because the system is less redundant, it is fully optimized. Even a failure of a single beam could lead to failure of the whole system. This could lead to failure of structure. Comparing this to a less optimum system, maybe you can call this as less optimum. In this, redundancy will be more. Because it is more redundant, this structure will have more members. Maybe there will be some members which are subjected to zero forces. Here the number of members will be more, and because you have more number of members, redundancy is more. Even if for some unaccounted forces there are some additional loads, a particular member could fail, but the failure of a particular member will not lead to failure of the whole structure. So in this case you have failure of structure will not take place and it will save lives. Optimum system will give you lesser steel requirement, but a less optimum system will give you more steel requirement, but it will save life. Optimum system will not handle any kind of error. Less optimum system will be able to carry errors. So a redundant system is better than an efficient system, because a redundant system allows you certain errors, but an efficient system will not allow you any error. Once all these points are clear and once you choose your final system, the next important point is the designing of member design. Let's move to the next step, member design. Engineering is a sequence, not a collection of checks. Structural design is a step-by-step logic. If early steps are wrong, later steps can never be right. Member design is not the starting point. Most engineers mistake this and always start directly with the member design. The correct order of steel design thinking. First, understand the purpose and constraints. Then choose the correct structural system. Then visualize the load flow, what will be applicable in your structure. Then decide the load resisting mechanism. Then go for member design. Most mistakes in steel design happen because engineers start at the last step. They directly jump into the member design. Next, designing member in isolation is dangerous. A beam is not just a beam. A column is not just a column. Every member interacts with others. A perfect beam in a bad system is still a bad design. Always, whenever you are designing a beam or a column, you should always consider the members which are connected with it. Next, connection behavior changes member behavior. Without deciding connection philosophy, member design is meaningless. In steel, you don't design member, you design member connection system. So whenever you design any member, it is not just a member in isolation, it is the member and connection between the member and other member. So always you have to think how the connection will be designed instead of designing the member in isolation. After this, the next step what you have to take into the consideration is stability. Stability check comes before section optimization. A lighter section is useless if it's unstable. An unstable member with higher capacity is still a failure. Always the stability of the system should be taken into consideration whenever you are designing a member. Finally, after designing the member, the next step which comes into the picture is connection design. Next step after member design is connection design. Steel structures fail at connection, not member. Most of the failure which occur in steel is because of connection, not because of member. Generally, when you design a system, the members are usually designed at lower utilization than compared to connection. It is easier to over-design a member but difficult when it comes to designing a connection. So generally, the utilization of connections is more than utilization of members. Hence, if failure has to occur, it mostly occurs at connection level and not at member level. Next important point in connection is the assumed behavior versus actual behavior. In a software, engineers often assume pinned connection, fixed connection, but in reality, there is nothing as a pinned or a fixed connection. It is either hinged or rigid. Let's understand the difference between pinned, hinged, rigid, and fixed. If this is the stiffness of the connection, theoretically we can define as pinned connection, where you will have zero moment in the connection, and you can define a fixed connection which will have resistance of infinite moment. But in reality, you do not have a pinned connection or a fixed connection. But in practice, you either have hinged connection or you have a rigid connection. Hinged connection is very close to theoretical pinned connection, and a rigid connection is very close to theoretical fixed connection. So these things you have to keep into mind. In theory, when you are assigning a pin connection, in practice you have to take care that at least you give a hinged connection. And in theory, if you are assigning a fixed support, you have to take care that at least you have a rigid connection in practice. Next important thing, connection detailing is engineering, not drafting. Many engineers misunderstand this and they treat connection as drafting and not engineering. So connection detailing is equal to engineering, not drafting. Many people treat detailing as drafting work and they don't consider it as engineering work. Bad detailing can destroy a good connection as well. Next step. After having a good member design and a good connection design, the next thing what you need to take into consideration is stability issue. Let's discuss stability. Stability, not strength, governs steel design. Most steel member fail by yielding. Steel has highest yield strength, but steel member are slender, flexible. They usually fail due to buckling, instability, excessive deformations. In steel structures, member rarely die of old age. They collapse due to instability. Now let's discuss global stability versus local stability. In local stability, we have member buckling, plate buckling, column flexure buckling, beam lateral torsion buckling. So all these checks have to be considered. Now what controls these local stability? To check these local stabilities, we check, slenderness ratios. We have section classification, cross-section classification. Then we have unbraced length. All these factors can be considered to check your local stability. Now let's talk about global stability. In global stability, we have sway of your member, overall sway of your member, frame instability, and most important, you have the speed delta effect, which is also called as second order effect. How to control this global stability? This can only be controlled by structural system, proper structural system, proper bracings, and proper load path continuity. So these global stability and local stability has to be considered in steel. Now let's discuss some of the typical stability mistakes which young engineers generally do. They assume pinned or fixed connection without checking whether these are actually practical on site. Sometimes you just model a connection, you just model a structure. Let's say you are modeling this structure and in this structure you are assigning fixed supports. But you also have to consider whether these kind of fixed supports are actually possible on site. Is it possible to give a rigid connection for these kind of supports? Trusting the default settings of the software, designing only for strength and not checking deflections, not checking the serviceable criterias. All these checks lead to failure in stability. If you consider all these factors, you can design a stable system. So these are the 7 points on which you should think before you start the design. Let's have a look at the mental checklist of a structural engineer. You should be able to answer all these questions before you begin the design. Do you understand the purpose of the structure? Is the structure system clear to you? Can you draw the load path of your structure? Do you know how each and every member behaves in your structure? Are the connections clear to you? Is your structure stable? Can this structure be easily constructed on site? Are the results of software matching with your expectations? If you know the answer to all these questions, then you are following the correct path. Today's video was about thinking like an engineer, not operating software. In the next videos, we'll take every concept you saw here and go deep, step by step, with real examples. If you want to be the engineer who understands why a structure works, not just whether it passes, this channel is for you.